Welcome to the second Q&A session on GSM architecture. So in this session I will basically cover the heart, the core of the GSM network, although we all know that GSM is a kind of a dying system, so no one invests a lot any longer in GSM. It's a second generation network that will be sooner or later replaced by 4G networks, 5G networks, whatever they will be. But as you will see in later sessions in this chapter, okay, even LTE reuses core components of GSM, or at least takes over parts of the architecture. So this is why I always emphasize that the architecture itself serves as a kind of a blueprint for other public land mobile networks. So I covered a bit the different components, and at least on this level you should be able to name the components to understand what they do, because later on maybe they are not called location registers anymore, but we will even see in LTE, oh, we have some kind of databases that manage the users. So this level of abstraction, I would say, is enough to understand the core idea. So once again, we have a so-called radio subsystem, and the names will change if we go from the second to the third to the fourth to the fifth generation. The names will change, but the basic idea, having a kind of a region, a part, a domain of the architecture that handles all the radio issues. And then we have a part that is the core network. Here it's the network subsystem with the operation subsystem containing all the databases needed for monitoring the subscribers, monitoring the users currently roaming into an area. This core network contains all the components that forward the traffic from a fixed network into the mobile network. So this clear separation of radio issues and core networks, this is what we will then see also in the other generations. Then you saw several slides about some more details in interfaces. If someone needs some more details about interfaces, well, look up the standard. This is nothing to, learn or whatever. You have to understand the basic architecture. And maybe just because there were some attacks on mobile phone networks, the interesting thing is that mobile phone networks, the classical ones, still use signaling systems. This signal system number 7, that's a packet switch system where you forward numbers, call setups and all these things. So the traffic flow that goes from the mobile here via a MSc to the network, but the signaling system, this is a signaling system introduced for digital fixed networks, and that's kind of a vulnerable system. So as soon as you have access to the signaling system, you can do some crazy things in the network. Okay, so that was the core of the GSM network. I talked about frequencies, also the separation, SIM and mobile station. So that was a key idea of the GSM architecture, that the SIM, the subscriber identity module, you see different generations here, is really separated from the device. So in some countries you still have devices there that are locked to a certain operator. We do not know this from the GSM network, but there are other networks where you buy the device from network operator and you cannot use this device for another operator. So in GSM from the very beginning there was a clear separation of this SIM that identifies the subscriber towards the network and the device, and you could just take out the SIM and put it into another device. So that was the basic idea there. Okay, now coming to the questions. Well, first of all, task for you. So you should be able to draw this basic architecture I just showed you. The classical system, you should know the functionality, because if you know this architecture, it is not that difficult then to identify, oh, now in the third or in the fourth generation, they replaced this component by that. So for example, in the fourth generation, we see that the base station controller and base transceiver station is replaced by one single component called eNode B with a similar functionality. But that means you should know the functionality of the base station controller and the base transceiver station. So that's the idea. So now to the first question. It's quite clear that you have to specify in a standard precisely the radio interface, because you have many different devices. But why also internal interfaces? Why do we have that many interfaces in the standards? If you look at the slides, you see so many internal interfaces. Why do we have to standardize them? In former times, this was not always standardized. Okay, one very good question. You can use hardware of different vendors. Exactly, there's competition. More vendors can produce. That exactly is a problem, that many vendors, so the hardware manufacturers, they try to lock you into a certain, I would say, ecosystem of their hardware, of their systems. So they say, okay, if you buy the VLR from me and the MSc and the BSc, then you have some nice fancy features. And this is indeed true. So that there are some special features you can only have if you stay with the same hardware manufacturer. But this kind of so-called vendor lock-in is a problem. It's dangerous. Not only because then they can charge whatever they want because you're already locked into this vendor, but also what happens if there is a software or hardware bug. I remember a day when in one of the German networks there was a real bug. They had hardware from only one manufacturer, so they had to fly in specialists from another country to solve the problems. Because they could not simply say, okay, we also have some other hardware, or if you do not fix this, then I will replace you by the other vendor. So this kind of vendor lock-in is a problem. So typically, to avoid, a whole zoo of different hardware systems, the operators, they stay with two different vendors, something like this, 2, maximum 3, but not only a single vendor. Because if this one, doesn't exist anymore, this also happens, then we have a problem. So typical vendors today, hardware manufacturers, are companies like Nokia, Ericsson. They were famous for mobile phones, but now they're really a big supplier of infrastructure and many more. So there are many of the classical IT companies, and they come and go. And there was in the early days, there was Alcatel, then bought by Lucent, etc., and Nokia, and. So you can follow this history, but you see usually you have two different vendors. And we will see this competition between the vendors and the manufacturers when we then reach the third generation. So that's exactly the case. So you can replace the hardware. That's the point. So if you look at the architecture of GSM, so this slide 24, is there a single point of failure? Where could there be a single point of failure? How can you avoid a single point of failure? So that was the slide 24. So could there be a single point of failure, assuming that we have all these nice things like whatever, maybe umbrella cells and things like this covering several other cells. So looking at this picture, so maybe what could be a single point of failure? Okay, if a BSC fails, that's a problem. So then you have a failure of a certain number of cells, and then there's at least the hope that maybe you have a larger umbrella cell, but the remaining part of the network will survive. So, but indeed, it is a problem, but that will not bring down the whole network. We had cases where the whole network was down, and that's okay, HLR database corrupted database if the gateway is down? Or, yeah, MSCs, it depends. So MSCs are responsible for, let's say, a big city or a certain region, then still the remaining part of the network survives. We had these problems so that certain regions could not use the mobile phone network, but HLR, that really is a problem. So what can you do against this problem? This is a database. So what do you usually do if a single database is a single point of failure for the whole network, to bring down the whole network? So what you usually do is a simple thing, but it costs money: redundancy. So, for example, in the very beginning in Germany, one of the big operators had 3 HLRs. So 3 different HLRs for Germany and with replicated data, but still there was a case that there was a failure in one of the databases, there was a software update in the other one, and the problem was then no one could actually reconnect to the network because, well, in the end, no one can register if there's no HLR. So that is a problem. The MSCs and all these components, also the databases, they have a pretty high reliability. So usually these are the telco components. They have a reliability of 99.99, at least 4 nines, some of the system 5 nines. So if you hear the term 5 nines, then this means after the dot you have these 5 nines of reliability. So basically almost always on. So downtime is a minute per year, something like this. These are systems where you can reinstall new operating systems without service interruption. And you can switch from one to another system without service interruptions, etc. So the classical telco systems, they are really very robust, high reliability. So that's different from maybe the consumer devices we use for our normal business. So the HLR, but still the HLR, that's a problem. If the VLR fails, then a region is down. But if the HLR fails, we have a problem. So you have to have at least one, but it's better to have several of these HLRs. Then another answer was, what happens if the gateway is down? Absolutely right. In the early days, there were some operators offering only a single gateway. So a single gateway is also a single point of failure. So you have to offer different gateways, but think of the networks. They have to know if one of the gateways is down. You have to reconfigure. In telco networks, so the classical telecommunication networks, this is well known. So if one link goes down, you can immediately switch over to backup links. And this works within milliseconds. So if there's a certain connection, whatever, someone breaks a cable, then the systems automatically switch over some milliseconds. In the internet, if you already listen to computer networks, you know this is not milliseconds. So it takes several seconds, sometimes even minutes, before the routing in the internet reconfigures the topology. So border gateway protocol, etc., etc. So if you heard of this, you know this takes longer. So if I talk about telco networks, these are the classical so-called telcos, the companies, the telecommunication companies. So in former times, you had a clear separation of the computer industry. These were the crazy guys from, Silicon Valley, having all these fancy ideas with new software and whatever, not always high reliable system. And you had the traditional world of telecommunication industry. Even in conferences, you could see this, the telco guys from telecommunication industry, like classic companies like AT&T, there were suits and ties, and the computer people, whatever, shorts and crazy shirts. So even in conferences, you could see who's from telco and who's from computer industry. 30 years ago, those two industries merged more and more, because from the classical telecommunication industry, so classical circuit switch networks, very expensive devices, but very high reliability, we saw more and more computers inside the networks. And the computers became more and more reliable. But still you see today differences. So call setup times, ISDN networks compared to a voice over IP video conferencing system. So there are still some differences. And when we cover the Tetra network, you will see that even in mobile communication systems, you have more conservative, more robust systems compared to the not that robust systems we sometimes use. So it depends on the usage scenarios, what you want to do with it. So telcos, that's short for telecommunication industries. So these are the classical circuit switch from analog networks, digital telephone networks, fixed infrastructure. And the computer people, well, they came up with many fancy ideas. And you also see this when you look at the communication protocols. So if you're familiar with the internet, you know the internet protocol, the heart of the internet, the IP protocol is a best effort protocol. So we cannot guarantee anything. The telco people, they charge money and they want to guarantee. So guaranteed data rate. So they in the early days, they hated the internet idea of, well, let's try our best effort. So like Ethernet, well, we try to transmit. No, telco wants to have guarantee, access time, maximum, whatever, 10 milliseconds delay or minimum 64 kilobit per second data rate. So that's a different world. And those two worlds, they came together. And so there are different waves going through this merger of telco and computer industry. And we saw more and more computer inside the telco networks. And today we see more and more of the classical schemes of telco networks inside the computer networks, because we need reliability. Suddenly we do real critical things over computer networks. But still, look at your voice over IP telephony client. It always says, don't use this for emergency calls. But what do you do in an emergency if you only have a voice over IP telephone? So these two worlds, they came together, let's say 30 years ago. And so now we hope to get best of both worlds. So that's the telco. Okay, talking too long. But please do ask, because then you understand much better the ideas behind this. Okay, back to a simple question. When you roam, where are you registered? You are roaming tourist, Australian in Berlin, from the US in Stuttgart or whatever. So in which databases is this roaming registered? VLR is one answer, HLR and VLR is another answer. So it is indeed registered first in the VLR because, hey, I'm new here. Then the VLR notice, oh, there's someone new. But then also in the HLR, because the HLR has to know roughly where you are, roughly. So the HLR knows the region, the location area where you are. So the HLR, absolutely right, stores the current VLR. So and it doesn't matter if it's the own network or a foreign network, correct. So if you roam, you're usually not in a network operated by the same operator where you at home. For example, here in Germany, you have 3 operators. So 3 real physical operators, not a virtual operators. But if you're somewhere else, sometimes the same company has networks there, but it's quite common that you roam into whatever network, in a foreign network, and then you're registered there at the foreign VLR and at home in your HLR. And it's quite important to understand that the HLR will not precisely track you. Think of millions of, in this case, GSM users, and you really want to track them, and then think back 80s, early 90s when the system was introduced. We simply didn't have the computing capacity to follow everyone. Today, that's a different story. If you look what the big companies like Apple and Google can do with devices, they can basically track you. with a very good precision. Because today, yes, we have enough storage, computing power, etc. So that's right. But GSM works without this precise localization. We'll come back to that. Okay, maybe we jump directly to this question. When I talk about localization, how can this be performed? Already, I would say mid-90s, there was one operator, it was at that time called FIAC Intercom in Germany. They offered something like a home zone, and if you stayed within the home zone, you saw a little house in your display, and that means you didn't have to pay for mobile usage. So they simulated a fixed phone. But how can you localize someone? How is this done? At least to a certain precision. So it's not wireless LAN fingerprinting you use today. I will come back to this when we cover wireless LANs. So how can you localize? And so how is this done? And how precise? Triangulation with different base stations. So triangulation, the term triangulation includes the word angle, and if you perform a triangulation, let's say these are the base stations and this is my mobile phone, then you have to know certain angles, so that you say, okay, let's say these are certain angles relative to whatever, and this is not feasible with the normal antennas. So the normal antennas cannot triangulate you, but, and sometimes these terms are mixed, there's something else that's called trilateration. Trilateration, that means I measure distances. Distances based on, for example, so I check the distance based on the flight time. So, flight time. Flight time, that means how long does it take in nanoseconds from a base station to a mobile, or the signal strength. Well, signal strength is not as good as flight time, but at least it gives you a rough indication. So trilateration creates kind of circles around base stations, and you're roughly at the intersection of the circles, plus minus. So triangulation measures angles. That's not possible with the simple antennas we use. Triangulation is possible with special antennas. Here in GSM, so we have to use something different. Flight time measurements does not work with this technology. This is what we do in our labs with ultra-wideband technology. Here doesn't work. So there were some other answers before I come to my answers. So trilateration is maybe something. GPS was not available in the early days. So GPS can be used today. So GPS or GLONASS, the Russian system, or Beidou, the Chinese system, or Galileo, the European system. So currently there are 4 major satellite systems available for localizations. And the chips integrated in your mobile phones today, they can use typically all 4 or 3 out of them for localization. Yes, but this works only outdoors, not indoors. So that's a problem. So in the end, before I come to the other answers, the point is, the only thing we can do with a simple GSM system without additional help is we know at least, just to make some space here, we know at least from a mobile phone the distance. Let's say here our mobile phone, well, not the precise distance, not the precise precision, but we know the mobile phone, for example, is attached to this antenna. Okay, then at least we know roughly, this is the cell. So that's the first thing we know. But that's not very accurate. So what else do we need? I told you in the slides that the mobile phones, to perform later their handover, they measure signals also from other cells, just to see if they are stronger. So if the mobile phone notices there are stronger signals, then they can ask for handovers. So by the combination of the knowledge you're somewhere in this cell, plus I receive signals from these two other base stations, you can assume, because you know the cells are roughly this and maybe roughly like this, you can assume the device is somewhere here. That gives you a precision plus minus whatever. Let's say plus minus 100 meter, plus minus 300 meters, so not very precise. Because, now coming back to one of your questions, because this is not very accurate. You have many reflections, you have multipath propagation. So think of, you do not have a direct path, but to your mobile phone you have a reflected signal with a lot of attenuation, or a direct signal and there's a tree in between. You don't know where all the trees on these planets are, so you think you receive a signal at a certain strength, and then you apply a formula. For example, signal strength is proportional, something like this, 3.5. So the signal strength somewhere proportional to this. But maybe this is wrong, because there's a tree, or there's reflection, or there's whatever other effects. So yes, you can do this, and this is something that's used for rough localization of mobile phones without accessing additional GPS data, because the GPS data is known only by the mobile phone and, for example, Apple, Google, those companies, if the mobile phone tells the companies the position. And that's done. So yes, those companies could localize you today with a higher precision. But for example, the classical way for the police for localization to follow a mobile phone is using the system, because the GSM network and all the others, they know roughly where you are. Not precisely, but roughly. So that means, okay, you are attached to this and that cell. But if your device is idle, you're not attached. So this is exactly when, for example, the police or the operator has to send an SMS, then the stations perform the paging, and then the device answers. And from this moment on, you know roughly where the device is. These are the silent SMSs. Okay, so angulation, lateration, etc. These are technologies we can use depending on the transceivers. That, by the way, is something now they try for at least roughly this also neighborhood. What device is my neighborhood? That's what you can do with Bluetooth. So it depends. The precision is not really high. It's a wireless technology. So yes, if you do angulation or triangulation with 3, then you can at least localize someone in a 2D plane. If you have 4 base stations, you can localize someone in a 3D space. If you have only 2, then the point is you can use only 2, but if you have 2 base stations and only 2, then you can imagine someone could be close to this intersection or close to that intersection. So it works, but you don't know at which of the positions. So it's just a system of linear equations you have to solve. So that's basically the point. And angulation only works if the device, let's say your antenna, can do this. So think of the MIMO technologies. MIMO, where you had several antennas and you had somewhere a device and you send out the signals and you receive the signals with a slight time shift, a shift in the phase of the signal. Think of a sine wave and you get this slight shifting. Remember when I talked about MIMO technology? And this is actually how you can get the angle. So if we assume now this is, now let's say, okay, we go for this antenna, then here we have a certain angle and we can calculate this angle by checking the phase shifts. So if you send and receive something, we also did beamforming, so you can follow someone using this beamforming, and this is where we can actually artificially create the signals with a certain angle. That means form the beam and follow someone, or receive signals and then calculate the angle of arrival. So that's called the angle of arrival, and you can calculate this if you have this special setting, not with an omnidirectional antenna. Omnidirectional antennas, whatever simple antennas, cannot do this, but with the help of several antennas you could do this. Or, and that's the classical thing, if you have a directed antenna. Maybe you know that if you look for wild animals and they have a collar with a sender, then you use this kind of antennas you hold in your hand, and depending on the direction of the antenna, because this antenna has a directive effect, you can roughly guess where the animal is. So where is the signal, where has the signal strongest power? So this is how you can actually get out the angle, and then you follow exactly this way, and you always check through different angles and check where the signal is really strong, where you hear this beep from whatever the tiger with this collar you're following through the whatever jungle, something like this. So this is how we get out the angles. But there was another question: how can I see my friends exactly moving if they share the location in the chats and whatever? And so the point is exactly the answer is already there. The localization is not done by the GSM system in this case, but the devices reveal their position to a provider. For example, they reveal the position to a company like Apple or Google or whatever. So the device itself tells the system, okay, here I am, and then the central system will tell you where the device is. So indeed, the normal mobile phone network has nothing to do with that. So that's something only on the application layer, and you have to enable your application that this application can forward your data. So forward the position data. And this is why many applications ask for positions. They do this also for marketing. They want to know where you are, but this makes you very transparent. So the phone network itself, it's way more restrictive and will not tell everybody where you are. And usually you need a decision by a judge before the police can access your position. Okay, it's different in case of emergency, etc. But usually you cannot access the position, but most of the users reveal their position. Well, that's your own free will to do this. So that's one of the things. So also your phones know a lot about their positions, either using wireless LAN, so-called fingerprinting, but you can also do it without, by checking the mobile phone cells. So all cells have a unique identifier. So if you hear a signal from a certain base station, this signal contains a unique identifier. That's a country code, that's an operator code, and with the help of this unique identifier and a database where it says, okay, this unique identifier belongs to this and that base station, you know roughly where you are. So in former times, the operators didn't want you to know where precisely the antennas are, but there are databases, so you can look this up. So in a so-called broadcast channel, your device regularly gets the identification of a base station. And that's necessary also for handover, because if you receive signals from other base stations, you have to tell the system, hey, although I'm right now attached to this antenna, I also receive signals from this and from that antenna. And then the system can decide to hand you over to the other base stations. So there are databases for that. Also databases of the operators, so the operators quite precisely know where their base stations are. So they also know the position, and so they can map this identifier to the position. So the normal mobile phone system works without GPS, works without any application, etc. And that's quite important, because you don't know which kind of application someone uses. And all these add-ons you're used to, how to find my friends, etc., they all use this extra information your mobile phone reveals. That's the idea. Okay, the question was, directional antennas have a similar effect as omnidirectional antennas. Yes, so with directional antennas, you can actually locate someone. With two antennas, well, as I indicated, with two antennas, you get the effect, two possible positions. But with three antennas, you can do the triangulation. So you can calculate the angle. This is what, for example, certain authorities do to find the location of a sender. So you use three cars, and then you can do this localization, or you use existing antenna systems. They will receive the signals, and then you can automatically do a triangulation across the country. Because we have so many antennas, you can easily find someone. So with directional antennas, that's easier. And this omnidirectional, then you cannot use the angle but signal strength, assuming certain signal propagation. So that, at least, that's the idea. Okay, so that's about localization. Then there was one question in between: how can we block stolen GSM phones? So you know, some people still steal mobile phones. How could we 100% stop stealing mobile phones? Well, you could still steal, but it's of no use. Yeah, you could have the list. There's this equipment identity register, and you could blacklist the device. And the point is that, exactly, you're right, there are two problems with that. One problem is you can change on some of the devices, not all of them, but you can change this unique identifier of the equipment. So then you have to, basically guess another identifier. But if you have a list of all legal identifiers, and so a whitelist and a blacklist, you cannot simply take over an identifier of another device, which would lead to blocking both devices. This would annoy someone, but at least you cannot just guess another identifier. So by listing the identifiers, whitelisting for allowed identifiers, blacklisting, plus, and that was the problem already many years ago, you have to exchange and merge all the lists across all operators. So there was one approach, I think it was in Ireland, when one of the network operators said, okay, let's bring together all our databases. We merged them, and then you cannot steal a mobile phone that is, used in one of the operators, and then take it away and go to another operator. The problem was, not all operators wanted this. Many reasons for that. One of the reasons is, if someone steals a mobile phone, you buy a new one. So, okay. And okay. The problem is the operators, they also, yes, they do not trust each other. So many, many reasons why we do not have a central database. So what is done today? The hardware manufacturers, they have their own mechanisms. Depending on the device you buy, there are some devices where it makes no sense at all to steal them, because unless you have the newest ways of hacking the devices, you simply cannot use them. So, but that's something, again, outside the network. So there was in the beginning this idea of blacklisting, but doesn't really work. So I remember my phones were stolen, I think 3 times, and you just forget it. You just forget it. And one of them was exactly one of these protected phones. So whoever stole it could never use the phone, but okay, now that's it. Okay, so that was a good idea in GSM, but never really used that much, this black and white listing. What you should have understood is why the separation between mobile station and SIM, because this was not the case in the early days of mobile networks, and there were also so-called SIM-locked devices. So again, please remember the core idea. I think I talked about this already today, that the separation is a quite good idea. In this context, well, answer, what is the problem or the advantage of the eSIM? I told you that more and more devices have an integrated eSIM. Some devices, like today's smartphones, they have still the traditional SIM plus an eSIM. Some of the devices have only an eSIM. So the problem exactly, and the advantage, you answer it. So the problem is that with the eSIM, you have another proprietary component in your phone you cannot remove. You cannot do anything if it fails. Yes, that's one of the point. And that's one of the advantages. If you have a SIM, you can really replace it. So you can change, basically swap SIMs, and you can take your personal data with you on the SIM. So this is a big advantage. The disadvantage of a real SIM card is you have to transport it somehow, because it's something real. You have to transport it, so it takes some days. So if the SIM is defect or if you need a new one, well, you have to wait. With the eSIM, you can simply, well, so to say, go to a new operator. You can even have different operators on the same mobile phone. So for example, you could have a SIM, a real SIM installed in your phone with one operator, and then simply download a new operator with all the necessary settings on your eSIM. So that's one way of doing this without any transfer of any additional device. But you're out of the control loop here. So something is installed in your device, and this is under the control of a network operator. And if hardware vendor plus network operator doesn't want you to use another operator, they simply do not allow the use of another operator on your device. So, for example, if you want to install a new or use a different operator in whatever mobile phone, no problem. Just use whatever SIM. As long as this is a legal and registered operator, you can use it. With the eSIM, nope, it does not work. Because some of the eSIMs together with the hardware, they're coupled. So you cannot, for example, on certain smartwatches, you cannot simply go to a different operator, because they have exclusive contracts between the hardware manufacturer and the network operators that this type of watch is only available for this and that operator. So as you see, there is a problem of having something really integrated. The big advantage is you can create waterproof casings, so because you don't have this slot to install anything. So the point is you have something installed in your device. And now there are many questions around this. So eSIMs, first of all, what about tracking, etc.? And if the phone is broken. So SIMs yes, SIMs can store part of your personal data, but they usually do not store anything that is related to apps. So everything that comes with your applications, that has to be backed up somehow, either local fashion on your PC at home or inside the cloud. So if really the phone breaks, you need additional backup from somewhere if you want to reconfigure a new phone. If the phone is stolen, including the SIM, you need additionally a new SIM together with a new phone. But if you have an eSIM, then you don't need an additional new SIM. You just need a new phone, and then you download automatically the configuration on your phone. This downloading of the eSIM is not under control of the operating system. So yes, the operating system can help, but the access of the SIM card can be done without the operating system. So, for example, without the operating system, you can download and install new software on the SIM, because the radio modem can directly talk to the SIM card. There's a so-called SIM application toolkit introduced already in the very early days of GSM, and this SIM application toolkit allows reprogramming of SIMs, and this is only with the help of a certain interface via the radio. So over the air you can reconfigure this. So you need certain settings on your SIM, network operator specific settings, like the access points, like certain addresses, etc. So this is programmed on your SIM during installation. So you install a certain profile on your eSIM, and then it can operate in the network. So many more questions. I'm sure I cannot answer everything. So possible SIM locking. SIM locking, that's something where you really have in your device a certain lock. Well, we all know, I hope these times are over, that you had SIM locks. That was in the early days when you got a phone relatively cheap, but you had to stay at a certain operator with the phone for a certain time. You notice that today you will not have these very cheap phones any longer. I remember days when you got a real expensive phone for just €1. But this was then a locked phone. You had to stay with a certain operator. Today you see you will not get in the end the phones for a single euro anymore. It's way more expensive, so usually you have to pay either directly once or monthly rates, whatever. You have to pay the full price. So this changed a lot, so that's quite different. So the point is, how do you lock, how do you access operating system level, how to circumvent? Well, this really depends on your device. So root access to the main SOC, so this is a system on a chip, does not always work. So for example, there are hardware manufacturers, they have a real built-in authentication between the chips, and you cannot simply directly access the chips. So they are protected, even you cannot replace single chips. So the chips are protected, and if you replace a single chip, it simply doesn't work. So, and they really try to keep their ecosystem clean. And you mention exactly one of the vendors, and they there you have a hard time. Yes, we know you can root your device, you can do many things, but so for example for smartwatches it is difficult. I would never say impossible, not at all, because rooting a mobile phone, that requires somewhere, let's say, a bug, or some call it a feature or whatever, but something in the software that allows rooting. And the hardware and software manufacturers, they try to keep their systems closed, because that depends on the markets. Then you're absolutely right. There are also applications, whole applications running on the SIM card. M-Pesa, is a payment system in Africa, very famous because many people do not have bank accounts. Once was in Kenya, and there, I don't know, 10% of the population has real bank accounts. But M-Pesa, run by Vodafone in the end, is very successful, and you can directly run Java on the SIM. So the SIM has now an operating system, and you can download programs. There's a processor in it, and it's a kind of a protected own computing environment independent of the mobile phone. So that's the point. So you're right, you see there's not only one solution. If you like it or not, the different solutions, well, that's your own decision. So that's a good thing that the market offers different devices with different features. Okay, but then what about some more questions about the eSIM? Could you buy a new phone only from network operator for the price they want and not buying the cheapest from Amazon? Try not to mention any names. But so the eSIM indeed is a way of, we will see what happens in the future, but this is something where you cannot that easily take out something, plug in a different SIM, and then the phone works. As I told you in former times, the SIM-locked phones were quite famous. That stopped more or less. At least I'm not really here in Germany aware of SIM-locked devices that many more, but they are more expensive now. But with the eSIM, well, this depends. So if the device manufacturer doesn't want you to download a certain configuration on the eSIM, you cannot. That's it. So that's exactly what happens at smartwatches. So, for example, as far as I know right now, that you cannot get the Apple Watch for arbitrary network operators here in Germany. Only the big ones have their contracts, and then it works only there. But you can, for example, use a smartphone and install different operators that allows you, for example, to roam in the subway from one operator to another one to get a better data rate. So that works. So you can use your eSIM there. The updates over the air, securing the updates. Yes, there are some problems. The over-the-air updates, at least in the early days, were not really secured. Why? Because no one thought that you can fake a base station. You need a base station and you need the whole infrastructure to perform this kind of update. So without the infrastructure, you cannot perform the over-the-air updates. But yes, it is protected. So these things, but there are certain not really proprietary. There are interfaces. They are also standardized, similar to DSL modems and fixed networks, where the network operator can update some settings on your DSL router. You can also update certain settings on your mobile phone without the operating system knowing this. For example, you could set certain things related to channels you use, related to whatever that is really at the heart of the mobile phone system, so radio issues, etc. Okay, so that's one of the things. So over-the-air updates, if you're interested in this, look it up. SIM over-the-air updates, SIM application toolkits, what you can do with a SIM. So it is basically an own computer. And so in the end, you do not really need the operating system. So you need the radio modem to receive everything. You can even reprogram this, and then this can then access SIM application toolkit. Furthermore, without that you notice anything, the SIM can control all your calls. So you dial a number, the SIM can then replace this number by another number. That's something to, reroute your calls. You think you call a certain number, but your SIM dials another number, and then your call goes to whatever secret service, and then they forward the call to the original number, and you will not notice it because your phone will simply call another station and not the one you wanted to call. So it's well documented, these interfaces, so you can replace certain numbers, things like this. Okay, And about zero-day exploits, please read the news. We cannot discuss them here, what you can do and cannot do with these devices. So yes, we know, sure, you can break into many things for good reasons. So I'm not telling this is good or bad or whatever. So it always depends on the perspective, what you want to do with your device. And in the end, you're right. If you use a smartphone, and especially if you enable all the tracking services, then your smartphone can be tracked and is tracked all the time. So if you use one of these nice messaging service or whatever, then you can be sure that the companies know where you are. Not the mobile phone operators. That's really a different story. And we all hope that the big companies like Apple's, Google's, whatever, do not do anything bad with the data, but it depends on the app you install. Wow, but that is... Okay, so we have to go on. I know there's so many things, but maybe we will have some more time. So can you update the modem through over-the-air updates without shutting down? Well, can you update the over-the-air so that it does not shut down when you shut down the phone? Yes, so basically you can do everything. Okay, because the modem is a computer on its own. The so-called baseband modem has a processor, has some more VLSI chips, whatever, is a programmable device. And so you can reboot the system. It has own operating system. You can reprogram. You can, well, maybe not you and not I, but in principle, you can reprogram these devices. And they can even directly access, well, certain parts of your hardware. Because, well, all the different devices, well, like the keyboard, display, whatever you have, or the memory, or the GPS component, they're all attached, connected to a bus system, so you can read the bus and directly read what's going on in the device. And the operating system is running on the main processor. So yes, it can also do many things, but you do not need the operating system for everything. Well, that's a difficult one. If law enforcement wants to know your location all the time, even if the phone is shut down, they could theoretically just update the modem to never shut down. I would never say this is impossible. I also do not say that this is done, because the point is, well, you can shut down your phone, your operating system, and then it depends on the hardware. What does it mean? Can you really run the modem on its own completely for a longer time and to perform these kinds of actions? Can you do this? We know of cases where you could eavesdrop into the communication microphone to the system and all these things. But the point is, to be honest, the devices are different, and there are companies offering services like this, but it's not that easy just to say, okay, now let's break into this and that phone. It takes a while. If you read the news, you see that even for quite powerful law enforcement agencies like FBI, etc., sometimes it takes time before they can break into a phone. There are companies that really have stacks full of all different types of mobile phones, offering hardware that allows you to break into a phone. But it's quite common that they need at least physical access for, let's say, 10 seconds or something like this. So they need an access, some kind of an initial access to the phone to install something, to download, to enable something. So pure over-the-air attacks. Well, yes, I would say, I would never say this is not possible, because it has to be worth it. You wouldn't do this for just, let's say, a normal criminal. But if this is real high-value target, as you write, then sure, it can be done, because it is a computer, and We do not know all the internals of radio modems, etc., what's going on. And the only thing then is to put away the mobile phone, to lock it somewhere in a metal cage or something like this. And this is why for many meetings you're not allowed to bring any mobile devices with you. You even have scanners in those rooms that scan for any radio signals emitted by any devices. So that's the point. So in the end, you're right, it is expensive and only some agencies or organized crime can afford this. But as you write, this costs millions. So zero-day exploits today, no matter for whatever operating systems, they go into millions. And it's a market. So I also downloaded once a price list for exploits, and then it depends what you want to do, if they charge several thousands or $1 million. So, and you cannot even really sue them. So if it doesn't really work. So, but it works. So, yeah. So there can be then many things, but really, I mean, to be honest, that's only worth if it's a high value target. Okay, but that's now more and more speculative. It's interesting, but we know that many things happen in organized crimes. We did some research there, but then some parts are speculative and some things we know from some of the devices. But okay, that's something different. Okay, we have to move on. After talking about the architecture, I went through the basic principle of multiplexing. So it's a TDMA scheme, but also frequency multiplexing for the duplex and for different channels. Then we had those single slots, and you should basically understand this picture. You do not have to go into, as always, into all the details, hierarchies, protocol layers. Protocol layers are quite interesting just for comparison. Well, how was the evolution between the second generation, third generation, etc. systems? So, coming up with some questions, not to bring you away from the crime scene, organized crime. That's very interesting, and we should do a seminar only about this. Why not next winter? We offered this already, so it's very interesting how you can hack the devices, etc. So why not? If you're interested in this, you're welcome. We can do this next semester in a seminar. And we also had so-called project seminars where you can program attacks like this on your own device or on special devices. Please not on other people's devices. Okay, so you should understand the ways where and how we multiplex, and then also to understand how GSM adapts to distances. I know this is more the theory boring part compared to all this hacking, but okay, if you're interested in this, just to come back to this, no problem. We can have a seminar on this because we offer seminar anyway. So we can do something like this. So we've done this already, and we can combine this with real devices and trying what you can do just to understand. I will not push you towards any criminal career. Please do not misunderstand this. We try to learn out of the weaknesses. We try to learn what the problems are, and then to better understand it, how to either prevent or how to open the system in a clear way. This depends on the perspective. So I would never say this is good or bad or whatever. So, but please don't do this with other people's devices. Okay, back to the real systems. So adapting to distances. You should understand this, how this works. What is the role of guard spaces? How can we adapt to distances? Because we will compare this then also with the third generation later on. Now, we have to say goodbye to all these interesting ideas. No, we have to go back to the things, how it works. How do we adapt? I see you all thinking of how to hack the devices. How can we adapt? Why do we need guard spaces? Think of this is a simple TDM system. and this also limits the radius of a GSM cell. No one idea what limits the radius? Well, think of, okay, signal. So we have our slots, time advance, exactly. And the signal should reach, for example, the antenna, the base transceiver station, somewhere inside this slot. And now if your mobile device moves closer or further away from the BTS, you have to have a certain guard space because you have reflections and this and that. So you have certain fluctuations inside the slot, but you pretty soon have to adapt the sending time by the time advanced field. The time advanced field has only 6 bits, and then you can count to a maximum number in the time advanced field, and that reflects roughly your 35 kilometers. So it's not the signal strength, well, also the signal strength, it should be still strong enough, but also the time advanced field, that is the limitation. So the time advanced field is not the guard space. The time advanced field is just a number, so 6 bits, and that's it. That's a field. You set, you check the distance because you can measure if the data from a base station, well, is still in sync with the slot or not, and from that you can calculate how long it takes for your data to send to the base station, and then you have to set the time advance field accordingly. The guard spaces, you do not control them. They're just there to have some, you know, some slack, some in between. So if your burst, how it's called, burst fluctuates inside this slot. So please do ask these questions because this helps understanding. So here in the figure, these are our guard spaces. You do not program them. They just happen because you do not know when this burst arrives. So this could be a little bit earlier, a little bit later. So you have some time in between. You see this is something like roughly 30 microseconds. You can compensate without reprogramming the time advance. So 30 microseconds, you can then think of how much this is, 30 microseconds. So 1 nanosecond, this is roughly 30 centimeters. That's the speed of light. So then 1 microsecond, that's 1,000 times 30 centimeters. So 300 meter, is it right? 300 meters, 1 microsecond. So you see, that's quite a lot. And if you have then 30 times, so that's quite a bit you can compensate in your guard space. But nevertheless, if you move further away, so that is good for reflections and all this, because suddenly you're driving and then you have line of sight and then suddenly a reflection, etc. But if you really move further away or you come closer, then you have to, well, set the time advance field to stay within this slot. So that's the idea here. Okay, that was about the limit, the radius, and then the maximum data rate. I don't know if someone calculated the maximum data rate. So if you look at once more on this slide, you see that we have every 4.615 millisecond, we repeat a slot, and inside the slot we have 114 bits. So 114 bits user data inside a slot. And we repeat this slot every 4.615 milliseconds. So by using all the bits as user bits, within one single slot, we can achieve a data rate of, did someone calculate it? Roughly, whatever. Something like 23 or whatever kilobit per second. So 23 kilobit per second, but what is offered is something like 9.6. Why do we not offer at least 20 kilobit per second, maybe some headers? Why not? What do we need the other bits for? Not everything is user data, that's right, but because sometimes you steal some bits for control data. So, but still 114 bits, even if we can use them all for user data, what else do we have? And this basically eats up all the remaining bits. You can share a slot, that's true, but even if we do not share the slot, let's assume we have 114 bits we can really use. So we can use in the uplink and downlink. What else do we have? And that's where all the bits go. So the point is, the difference is forward error correction. So basically, we have to insert a lot of redundancy plus some frame structures, headers, etc. So we need a lot of forward error correction. Depending on the interference level, GSM allows only also sending 14.4 kilobit per second using a single slot. We'll come to these higher data rates. But if there's some more interference, we need more redundancy. So redundancy basically eats up all the remaining bits. So that's really a problem in wireless communication. So you have certain frame structures, headers, etc., but also redundancy. So that's our problem. Forward error correction. Sometimes, for example, in Bluetooth, we will see systems where you send the same data 3 times. So you send identical data 3 times just for redundancy because the bit error rates are that high. So the point is that you steal bits for control data. So you cannot use all the 140. So from time to time you steal some bits. Plus you have some header structures. So user data rates, that means really the data rate you can use in the end. So stealing some of the bits, then having some packet headers, for example, or some headers, checksumming, if you use checksum, plus forward error correction redundancy. So this all contributes to these whatever 13 kilobit per second. So indeed, you lose a lot. That really is a lot. So that is really a problem. So as I said, in Bluetooth, there are situations where you send the same data 3 times. So the data rate is only 1/3 of the data rate the system offers. So yes, indeed, a lot of redundancy. Okay, so what you should understand is this basic idea of multiplexing. Again, not all the protocols. That is way too much. And similar is true then for the final part of today. That was this mobile terminated call. Well, as you saw when you followed the video, there are many steps involved. So basically it was this call is redirected here, and then the gateway checks with the database, oh, is this really a subscriber? You check with the region where the subscriber is, you get the answer back, then you forward the call using a topological correct phone number, then the MSc doesn't know where it is, then you do this thing that's called paging to these huge regions, and then after this paging reaches, well, many devices, thousands of devices, so each time a phone rings, also your phone received the paging message, but only one will answer, hopefully, hopefully the right one, and then you will perform some security checks before you then forward the call. That was the basic idea. So please do follow again these different steps to understand, well, really this takes long. But also you can imagine that maybe that calling other phones also drain your battery, because your phone also has to check, oh, was this paging for me? Oh, no, it was not for me. So maybe in crowded cities, the battery doesn't last that long compared to the countryside when you stay close to a base station, because the distance is also quite important. That was one thing I explained in this section. And then also the idea of handover, where one signal gets weaker, one stronger, and then at a certain point in time we perform the handover. And this handover was then explained here is a so-called hard handover, because there's a certain point in time where we really switch. We switch from one BTS to another BTS. So we switch over. We cannot simultaneously receive data from or send data to different base stations in GSM. And that's different, for example, to third generation, where you can actually do this. So this is why we have here a so-called hard handover. Some questions to this. So here again, just to remember you how we covered this already, how the localization works, because after this section you understand this. Oh yes, there was this. We don't have to go into this again. You understand this measurement. So once more, localization is based on the received signal strength. And the mobile phone always measures signal strength to different base stations. And the mobile phone reports the signal strength. Reports the signal strength to the base station it is attached to. Reports, oh, I see all these other base stations. And this is exactly when I talked about these measurement reports, measurement results. And then inside the network, the base station controller, for example, does this handover decision. So this question should remind you once more about this localization without the help of any GPS, anything else. Okay, now to a new question, handover margin. Why do we need this handover margin? Why don't we simply switch over when another station is stronger? Flipping between stations, so you might switch back and forth. That's exactly the point. When your signal from your current base station gets weaker and weaker compared to your neighbors, you do not immediately switch at this point where you cross the signal strength of the other. One reason is already indicated in signal. You have not really these nice figures. This is just if you take the average. So you have to smooth the signal strength. And if you switched over at exactly this point, you could create, by switching over, more noise, weaken the signal, whatever, and you could flip back and forth and back and forth. And as you saw, this takes some time. And this also puts some load on your system. So flipping back and forth is a problem, and you might even lose the connection. So there are sometimes situations where you cannot go back into the cell. Maybe it's now fully loaded, or sometimes situation where you cannot make the call setup fast enough. All these things. So you try to avoid this, because maybe you also move back into the old cell. So why then switching to a new cell if you just stayed, let's say, at the overlapping region for some time and then return to your old cell. So you always try to avoid too much load on the system. That's a problem. So now you saw, okay, we perform handovers, we can call phones no matter where you are. I gave you also examples why you might hear some of those cracking noises in the loudspeaker. These are the signals your phones send, depending on the type of the phone, stronger or weaker. Now a question, where does the system really store user-related data? You will find many different places where you leave actually your traces. It's not only the databases. And it's a question if it's user-related, and the system also tries to anonymize you somehow in the system. So where do we store at least some data? So if you look at the mobile terminated call, also mobile originated call, but also handover procedure, so there's some more entities, not only the HLR and VLR, where you can find some more information about devices, about users. In the end, also in the SIM, SIM definitely has some user-related data, but who else knows from your existence and from the existence of your device? Authorization knows at least that someone asked for something. I will cover this in the next session, how this works with authorization, but also the base stations, the MSCs, exactly. So all the base stations, well, where you are, they know at least an identifier, and this identifier can be mapped onto your device, and this can be mapped finally onto you, because, well, you have to authenticate, as we learn in the next session. But the system itself, as I showed you on this slide about this mobile terminated call, the system here has to store information about you in the HLR. That's your, I would say, your contract and whatever the system knows about you. This system, the VLR, knows your rough location, contract, but the HLR also knows location. Then, furthermore, the GMSC knows your phone number, but then also knows the mapping of this phone number to a mobile station roaming number, because, well, you have to forward the call somehow, so the MSC also knows a temporary identity of you. You know a number, so you know at least there is someone. The MSC in a foreign network doesn't know your name or whatever. This is not important, but knows a temporary identifier. And the base station then also has to know at least the identifier, so to know, okay, this device is now allowed to whatever access the network. So you see there in all the different components some traces of your device. So that's quite important. So all the devices, all the components know something about your device. And with the help of the HLR, you can bring together names, subscribers, persons to devices at certain times and locations. So normally you or the devices inside the network cannot bring together this information, but if needed for some court decisions or whatever, you can bring together this information so that you know who actually used the phone network at which time, using which cell, etc. Well, you know don't know exactly the person, you know the right SIM. So if someone actually steals your phone and it's still unlocked and uses it, you don't know who this is, but you know this is the SIM and this is the device. So that is quite important. The network has to know quite a lot that you can, in the end, also for charging. You have to count the minutes, or you have to count, when you come to GPRS, you have to count the bytes you use, and you will be charged according to your contract. So this should just show you leave a certain trace across the whole system. And then it depends on the national laws, how long you can store this information, when you delete the information. So it's quite common to store the information, let's say, for 30 days. And then you do this charging billing thing, and then you can delete the information. So it depends. But as you know, storage does not really cost that much. So, okay, you could do many things. So the mobile station itself also has information about the environment. That means the other base transceiver stations, the networks, etc. There are many more information, like where are broadcast channels, what are the frequencies, etc. But this is not really related to the user. So this just should give you an impression of that you need a lot of information, parameters, etc., just to follow a device, just to keep track, just to know where it is, just to forward the calls. Okay, so I know that was quite a lot of material, especially the first part of today that covered several slides, but that should give you a good impression of the different components of this system. And that's basically all about the real architecture. I know we have something left: higher data rates, security. I will come back in the next Q&A session to this. We'll cover also more reliable system before we then go into the third generation system. So it was a bit more for today, and for the next time it's a bit less material compared to today. But then we can also wrap up the whole GSM system. And as I told you in the very beginning, this is a system that is not really rolled out anymore, but will be there, I don't know, maybe for the next 10 years, but the core components will be there for way longer because you reuse them for many other systems. Okay, do you have any more questions related to the architecture, to the basic concepts of GSM? Okay, I don't see any questions right now. Okay, so thanks once more to you all, and then we hear, read, see, whatever it means today, each other next week. Stay healthy and see you. Bye.